Chapter 7 is a topic many designers find interesting. We're talking about engineering design, the selection and application of SPDs, what we call power protectors. But SPDs have seen explosive growth, especially in the last 5 or 6 years. Many domestic brands have emerged, indicating we have a very large market regarding SPD applications. We must first clarify a concept. What's the purpose of SPDs? What are they protecting? They protect against overvoltage, specifically transient overvoltage. There are two types, transient and temporary overvoltage. Transient overvoltage appears as sharp spikes on 50 Hz waveforms, like burrs. Examples, atmospheric and switching overvoltage with similar waveforms. Temporary overvoltage has unchanged frequency, just higher amplitude. These are different types of overvoltage, requiring different protection. For temporary overvoltage, we use specific protection methods. There are many causes, which I won't detail. We typically use overvoltage protection components for 220V appliances. Household devices are sensitive to temporary overvoltage. A broken neutral wire can cause overvoltage exceeding 220V. So we need special overvoltage protection in terminal circuits. I heard residential codes now require this protection. It's been a while since I studied the specifics, but I recall the component. This is for end circuits, but for transient overvoltage. Two forms, atmospheric, very high voltage, up to 20x normal, rated voltage, and switching overvoltage from contactors, switches, and breakers. This will cause voltage fluctuations or shocks in the system. Both atmospheric and operational overvoltage will cause equipment aging. Severe cases lead to insulation breakdown and burnout. So let's take a look at how atmospheric overvoltage from discharge intrudes into our building's interior. This is in our standard 50057, the Building Lightning Protection Design Code. There's a diagram. I remember 3 types. 1 through overhead lines, direct conduction intrusion via overhead lines. Second, through the building's lightning protection during the ground discharge process. Down conductors with high current flow produce strong alternating magnetic fields. Then in our building's internal circuits, power systems, including low voltage ones, can induce relatively high overvoltage. This intrusion method is called inductive. It's known as inductive intrusion. There's also nearby lightning strikes, like tall flagpoles or trees near buildings when struck by lightning. As large currents discharge to ground, it causes a sudden ground potential rise, an increase in ground potential, and our electrical equipment's outer casing is connected to earth via grounding, is linked to the ground. So the sudden ground potential rise travels through the grounding wire to our equipment's outer casing. This sudden casing potential increase stresses the equipment's insulation, causing reverse breakdown. This effect is called backstrike, so intrusion, induction, or backstrike all affect our equipment, especially sensitive electronic devices, causing significant harm. So what can we do to prevent atmospheric overvoltage? Focus on overvoltage prevention. It's a comprehensive measure relying on the building's lightning protection. To achieve this, not just one component alone, not rely on one of them. For example, to say that adding an SPD is all over. No, the refueling protector is only one part of these 7 major projects. That is, we as the entire external and internal lightning protection project is divided into 7 parts, including connectors, down wires, grounding devices, shielding and other positions, reasonable wiring, and SPD. So SPD is necessary but not sufficient. That is to say, everything is okay with SPD. You also have to have a very reasonable, complete building lightning protection. So this is also a definition of lightning protection zoning in our 50057. That is to say, it is outside the protection range of our lightning protection, such as the lightning receiver. We call it LPZ0A. But the one that is outside the building is called LPZ0B. The difference between 0A and 0B is nothing more than that 0A is susceptible to this kind of direct lightning. However, since area 0B has a flash receiver, it will not be directly mined. But in the lightning strike of the electromagnetic pulse, it is not attenuated and will be completely affected. But after the exterior walls of my building and this reinforcement inside the exterior walls and so on, its shielding effect is attenuated to a certain extent. Entering the LPZ, one area inside the building will not be attacked by direct mines. At the same time, the electromagnetic pulse of its lightning strike will also be weakened and attenuated. In the same way, when I have a separate room inside the building, and there is a certain amount of shielding at the time, it further de-attenuates the electromagnetic pulse of our lightning strikes in this LPZ2 region. The energy has been further weakened. So, according to the IEC and the National Standard 50057, it is the dominant ideology, SPT, installed. In what place is it installed? In 0A, 0B, LPZ 0B, and Zone 1 on this interface, as well as Zone 1 and Zone 2 interfaces, and Zone 2 and beyond. There are some subsequent partitions on this interface. Of course, it's not like we're digging a hole in the wall on the diagram, put the SPT there. Instead, it can be installed on the distribution cabinet and distribution box that are set in the power supply closest to the power supply inlet. So I'll briefly talk about the principle of SPT. If we don't add SPT and a surge comes, we amplify the voltage glitch through a filter. It becomes a typical triangle wave. Due to its high peak value, it can easily damage sensitive equipment if applied. So what can we do? We use a limiter to restrict the voltage peak to a certain level. For example, SPT can limit a 4000 V surge to no more than 1500 V. My equipment's voltage tolerance is 1500 V, so this way our equipment is safe. That's basically the principle. That's the principle. How is equipment voltage tolerance defined? It's in IEC standards and our national standards, like in 50057 or 50343, which provide tables categorizing voltage tolerance into 4 levels, corresponding to 1.5 kV, 2.5 kV, 4 kV, and 6 kV. The most vulnerable are electronic devices like audio, TV, computers, etc. Their voltage tolerance is very low, so they're often our main protection targets. They're our key protection objects. For motors and switches, however, their voltage tolerance is much higher. They're not our main protection focus, and they're not as valuable as sensitive devices. Right. SPD definitely protects low voltage tolerance, sensitive devices, and high value equipment. SPD works like a valve. Without a surge, it's high impedance. The circuit is in an open state. But when a surge occurs, it quickly becomes low impedance, conductive, directing current to ground quickly, while limiting voltage at both ends. So voltage at the device ends is much lower. Much lower. By placing this at the power supply's front end, it can shield or block current and surge voltage from reaching the device, acting as a barrier. SPD has many electrical parameters. I'll cover ones you might encounter or have questions about. In discussing SPD, we'll mention if it's for class 1 or 2 experiments or if it's a T1 or T2 type product. So what exactly is a T1 type product? It uses a 1350 waveform impulse current for impact testing to see if our SPD can effectively discharge and withstand damage without failing. This energy level is extremely high. The 1350 waveform simulates direct lightning strikes. When we test SPDs this way, it's clear the 1350 waveform mimics direct lightning, while the 820 waveform simulates induced lightning. That's voltage induced in power systems by lightning class 2 tests mainly use 820 nominal discharge current. Class 3 tests use a combined waveform. It includes both 1250 voltage waveform and 820 current waveform for comprehensive testing. So, what can we say? Class 1 SPD tests often prove the SPD's conduction capacity. This capability is very powerful. SPDs that pass Class 2 tests are mainly for induced overvoltage protection, so they're not used for primary protection, but in secondary lightning protection zones. Class 1 SPDs have strong conduction and discharge abilities. They're designed for direct lightning simulation, so they're best for primary protection in distribution cabinets. Electric protectors have many electrical parameters, including Inimax, Impulse INIP, and INF relate to product characteristics, not performance factors in design. So we won't discuss those further. The first three are relevant. Design standards mention these when selecting SPDs. We should focus on its Inimax IN, and IMAX are for Class 2 experiment SPDs. SPD has this parameter. Impulse is for Class 1 experiments. It represents the max impulse current it can handle. IN and IMAX are to help understand better. I can use an electrical parameter of a circuit breaker for comparison. Let's make an analogy. IN, as it must withstand multiple 820 waveform currents without damage. It's similar to the ICs of our low voltage circuit breakers using segmentation, while IMAX only passes through once it's exceeded. That's it. It's similar to the ICU of circuit breakers. So this IMAX value is often very large. Usually IMAX equals twice the in IMAX is twice the in. There's also you see residual voltage, limiting voltage, UP itself. Most important here is UP value, which is for the SPD I chose. Besides strong discharge ability, I require good conduction. It should conduct high lightning currents sufficiently. During conduction, its residual voltage shouldn't be too high, because if residual voltage is high, what happens? It transfers to device terminals, adding to its coil. If UP is high, it can still damage device coils. It's like installing an SPD that doesn't work. So what's our ideal SPD? Higher discharge current is better, lower up value is better, but that's ideal. Due to SPD's structure, it's contradictory. I want strong discharge current conduction. The corresponding UP value might be high. If I limit up, discharge current drops too. So what do? How to solve this? We often need graded protection. Don't expect one SPD to solve all problems. We often need multi-level coordinated protection. SPDs use many types of internal components. For example, what are ideal characteristics? Some use varistors, gas tubes, and sensitive resistors. Currently, sensitive resistors are common in power SPDs, often combined with some gas discharge tubes.